So, welcome back, everyone. This is going to be the last Science 10 lesson, and we are focusing on one unit in this entire lesson called Energy Flow in Global Systems, also known as a climate unit. And this unit takes aspects of chemistry, physics, and biology, but overall it is very simple, and it is mostly just thinking questions. There's not a lot of like facts and things you need to memorize. So you should be good in this unit. Keep in mind that this unit does not take very long to do, and it can be summed up in roughly 5 minutes, but we are going to be a little bit more in depth than that. And hopefully you guys have a good understanding of this unit, but just keep in mind that it's a simple unit. So even if we do fly by something and you're like, oh, I don't really quite get that. Well, it is what it is because it's probably not that important. Okay. So let's let's begin. So biosphere and climate. So we're just going over some key terms right now. Okay. So it gives us two pictures and it asks which one is weather and which one is climate. So you would often hear someone say, "Oh, I like the weather today. Oh, the weather's really bad today." Well, the weather can fluctuate um day by day because weather is a daily type of measurement for like the daily temperature and conditions of where you live. But climate is an overall, an overbearing, like a trend in the weather that you experience. So I would say that this is weather, and I would say that this would be climate because I don't think that a tornado would be an everyday type of thing. It's a fluctuation. It happens and sometimes it doesn't happen. And this is like an overarching thing. Like probably in this prairie, the weather's always like this. That's why you can grow like so much of this grass and stuff. Okay. So let's see if I'm right. Mouse. Okay. All right. So this is weather. So weather is defined as conditions of temperature, air pressure, cloud cover, precipitation, the humidity, that occur at a particular place and a particular time. So, like I said, it's a daily occurrence type of thing, and it can fluctuate a lot. But climate is the average weather conditions over a region of area over a long time. So it's just the general idea of the weather there. So if we hit a snowstorm in the middle of the summer, we're not gonna say that, oh, the climate is really cold. We would rather say something like the climate is pretty hot in the summer because obviously we don't get a snowstorm every day. So it's an average. So you need like evidence to support your claims on describing the climate. Okay. Let me clear my drawings. Okay. Mouse. Okay, wait, hold on. All right, so this is Southern Alberta, summer of 2015. These are just pictures. So now we're on some actual notes. Yeah. So the weather and climate, right? They interact. They are interactions of different parts of the biosphere. So the biosphere is just where it's just life, where the earth on life happens, and just the naturey aspect of it. So a more scientific term is written here. The parts of earth that have conditions suitable for supporting life. It is made of three parts. So it says two out of the three parts here. So the three parts are the air. Oh, okay, well, wow, I don't know how to use that. Okay. The air, the water, and the earth. So atmosphere, we all know that's the air. Hydro meaning water, and then lithosphere. That's just something you need to memorize. And they interact each other all because of the energy from the sun. So the energy from the sun can help the water cycle. It gives plants and animals a place to live, a suitable habitat to live, and our air can trap in the sunlight to heat the earth up to a certain extent and protect us by giving us warmth. All right, so now we're going to go through the structural zones. Okay, so I believe we just went through that part, so we're good. All right, so let's go over the atmosphere in detail, right? So the atmosphere is just air, right? But what is air made out of? Surprisingly, it is made out of only 21% oxygen, but 78% nitrogen. And you don't even know any specific data like specific numbers for this unit, but you just need to know, the general trend of it. Okay, and the atmosphere is around 500 kilometers out, and if my memory is correct, I believe the first 10 kilometers is like um where we live. So I don't know. That kind of surprises me because 10 kilometers, you wouldn't think that's a lot, but that is the amount of air that we need to live in. Okay. All right. So these are the layers. All right. So this graph is just showing the temperature and how it increases and decreases per layer of atmosphere. So the way I remember it is it always goes hot, cold, right? But what if you don't remember it, whether it goes cold first or hot first? So I just think of uh, as you go higher, right, you get colder. So I just think about Mount Everest. I see it right here, and how on Mount Everest, it's really cold. So that's why I know it goes from hot to cold, and cold to hot, and cold to hot, right? Sorry. Okay. So the layers are called, well, this layer is called the troposphere, the stratosphere, the mesosphere, and the thermosphere. And it's not really important, but this is the one where we live in. This has ozone in it, and ozone traps UV radiation from the sun, so it's very important to kind of know what's in there. This was a pretty irrelevant layer of the atmosphere, and then this is called thermosphere, and it has aurora borealis. It has aurora borealis, and they're like these like streaks of light caused by like the magnetic field interacting with the Earth or something like that. Like, yeah, basically the unit to me is just something like that because they give you very simple understandings of really complicated things. All right. Oh, look. See, deflected by the Earth's magnetic field. So these particles accumulate at the poles where they excite air molecules to produce beautiful streams of plasma called aurora. Okay. The definition that they gave us was pretty standard. Not very helpful, but just deal with it. All right. Altitude and temperature. Okay. So altitude is how high something is, right? So as your altitude in our troposphere, right, in the place that we can survive in, as the altitude increases, right, the temperature decreases. All right, that is why there's snow on mountains and why it is really hard to breathe because there's not a lot of air. Okay, so Earth's temperature, Earth's atmosphere. All right, I don't know why it said Earth's atmosphere. And then the next slide was lithosphere. All right, so lithosphere is our Earth, and obviously there's like the actual Earth, like dirt, terrain, and water. And under that is all the lava, right? You don't need to know all these terms and stuff, but lava, Earth, and then beneath that is the Earth's core, which is like metal or something. So just know that it's core. It goes from hard to soft, essentially. Okay. So why? All right, hydrosphere. All right, so the ocean is the hydrosphere, and all of Earth's life depend on water to some extent because we need it in our body and we need it to grow. So your body utilizes water and water. Okay, and 97% of it is salt water, 3% is fresh water. Most of it is frozen as mountain glaciers and continental ice sheets. So this basically means is that like we should be watching out for our water consumption because we don't have a lot of water to use, and we have to go through a lot of processes like filtering them and whatnot, and it requires a lot of technology, money, and resources. So it is best to conserve water just in case in the future where we don't have any fresh water left, and we have to do all of these things. All right, so adaptations, right? Adaptations are changes that animals or that organisms make to respond to stimuli in order for them to survive in a situation. So, a cactus, a lily pad or something, a fox, and a elephant. Okay, so describe the climate that goes with each adaptation. So, I believe the fox lives in a cold climate, so therefore, if it's cold, it needs something to keep it warm. So that's why it has fur. Okay. The elephant lives in a very hot climate in Africa and it has big ears. So these ears can act as fans or it volume. Did you touch on surface area to volume ratio in bio? Hello?
Yes.
Okay, yeah. So the surface area to volume ratio of the elephant ears allows the heat to be like taken out very easily, like diffused very easily, very efficient. And then the cactus lives in a dry climate, so it will so its leaves are flat because once again there's a lot of heat. So so okay, so fat leaves prevent water loss. Interesting. So it lives in a wet climate, so air-filled bladders for flotation. Okay, this was a pretty bad picture. I don't know why they put that there. All right, large thin ears maximize heat loss. Okay, and then cold tiny ears prevent heat loss. Tiny ears. What is okay? Um, very interesting. But yeah, let's just move on. But yes. Okay, so radiation, all right, new term defined as the process by which solar energy reaches the Earth, right? So, oh my God, why does it keep going there? Okay. All right. So, in simpler terms, it just means um the light that comes from the sun. Like that's it. Radiation. And then this radiation can can be of different wavelengths of light, and these wavelengths do different things. Like ultraviolet rays are like all UV light, right? That can mess up your skin and all this stuff, and infrared, things like that. Okay, let me go to the next one. All right, so this is just a quick diagram showing you what happens when sun from the light reaches Earth. And I really hated this diagram when I was looking at it because it was really confusing and the percentages never added up. But I believe it's 19%. So if I remember correctly, like when I finally understood it, oh my God, I think this meant, what is happening? Okay. This meant 19% is absorbed in the atmosphere, 51% is actually used, and then 30% is directly reflected up. But then here's the problem, right? If we go to the next slide of this data, it says that 9% is reflected, 49% is absorbed by oceans, and 42 is used in the atmosphere, which is like very different from what the last thing said. Sorry, what the oh my God, from what the last thing said. So I don't know which one to go by, but honestly, I would probably go by this set of data, because the teacher made this, so they probably have a good understanding of what's happening. Okay. Okay. What causes different seasons? All right. Well, to put it in simpler terms, the Earth tilts on the axis and it leans towards the sun at different angles. So if you live on this part of the Earth and the sun's pointing here, well, it's going to be hotter, so it's going to be summer. And then if you are living on this side of the earth, right, it will be winter for you because because you are not closer to the sun, so you are not getting the same heat that you get from the sun. So that's a pretty simple way. And what determines is that the earth rotates in a circle, different positions, but however, it also rotates on its own axis. So that's why you either end up on here or on here. Yes. Okay. So now, what does adding salt to water change how fast it boils? So I don't ever remember doing this question, but I believe salt does speed up how fast it does speed up when you add water. And the reason why it adds up is because um hmm why does it add up? I'm pretty sure it has something to do with the fact that the salt is attracted to the water and it traps it in so then it's easier for it to boil. But yeah, I searched it up and it just said that. So yay. Okay, let me erase my pictures. Oh, more pictures. Okay, so now we have a term called albedo. Albedo is how much light is reflected by a surface, right? So things that are white, they reflect light and they reflect light more, and then things that are black, they absorb light. So that's why when you wear a white shirt versus the black shirt in the summer, you can feel the different temperature. So for here, this will have high albedo because it's white. And for this, it will have low albedo because it is dark. Pretty interesting concept. Okay. So when light is reflected back to the space, it can have global cooling effect because you are not absorbing the light. Correct. Okay. Natural greenhouse effect. Okay, so you've probably heard of the greenhouse effect thing, and you're saying that it's due to global and greenhouse gases cause global warming, right? Right. No, sorry, I got distracted by something. But yeah. So the way it works is like you have the sun comes in, and then there are certain greenhouse gases that like specific chemicals, and they just trap the sunlight. So then it gets really hot because now there's more sun, right? And that's basically what this picture is saying. Okay, infrared. Without greenhouse effect, the Earth would be completely covered with ice. This is also true. With You need a certain amount of heat to sustain life. All right, all right. Oh, wait, wait. Something came up. My bad. Okay, let's move on. Okay, so a region's climate is determined by how much sun hits it, right? And at the equator, the at like so equator, so like African, South American countries, rainforest, it is hotter because more light hits it. So if we look at a sphere, right, we can see that it narrows out from the top towards the bottom. So the light hits it, so more light will hit it here than compared to here because it is wider and it is closer. Okay. Clear all drawings. So what causes different seasons? Okay, so some people think that Earth is closer to the sun in the summer, but winter, but that's not true, right? Um, it's just because of the tilt. So it says that second last sentence, since Earth is tilted at different concentrations, sunlight reaches the surface, and that is why our seasons are different. So let's look at this for example. Um, we're looking at this perspective, by the way. So this land, right? So from here to here, it's close to the sun. It's facing the sun. Therefore, it is summer. From here to it is not. It is on the opposite side. So this is winter. And then it shows you here because it's half and half. Like you see how it's kind of split apart. That's that's called a equinox. So an equinox is when you have equal hours of sunlight and darkness per day, 12 and 12 hours. Okay, let's do it. Okay, we went over that. All right, heat and the hydrosphere. All right, so why are we so good at preserving our climate on Earth? Well, we have water that surrounds the Earth. Okay, so for example, water can store a lot of heat because it has a high specific heat capacity. So what this means is that it means that it needs more energy, so more joules to heat 1 gram of something of this thing we're talking about by 1 degree Celsius. So joules per degree Celsius. Water specific heat capacity is 4.19. I think this is the no, this is the regular value. Okay. If you're an IB, you use 4.18. Okay, I don't know why, but because it needs so much, because it takes so much energy to heat it up, um, you aren't really able to like, I believe, heat up the earth that fast, and the water helps keep a lot of energy in it. Okay. And because there is a high specific heat capacity, we can absorb more water in, right? Because it takes a lot of energy to heat it. So we can actually take in a lot of energy. We can take in a lot of energy before it being too hot. All right. All right. So water. Let's just go over some water unique properties because we love water and we learn about it in every subject except for physics. Okay. So water has cohesion, a lot of cohesion. So water molecules are attracted to each other. And this is because of a chemical property where the polarity, so one end is more positive than the other end. So something has a positive side and negative side. So this means that that other water also has positive and negative side. So this positive is attracted to this negative, and this negative is attracted to this positive, and like there's a lot. So it goes this and this. Okay, bad drawing, but you get the point, right? Um, that's just a unique property, I guess. But in chemistry, you'll learn more about this, and it's actually a pretty interesting topic, in my opinion. Okay. So the cohesion comes from the hydrogen bonds because of the attract. Oh my god, hold on. Cohesion comes from hydrogen bonds because of the attraction between the positive hydrogen atoms and the negative oxygen atoms. So one positive side, one negative side. Yes, this is positive, this is negative. Very good picture. Okay. So water has surface tension, an attractive force between molecules on the surface. This is also a property. Um, if you ever put a, if you ever put like what is it called? If you ever put a water on a coin, it will form like a little like ball on top because of the surface tension. And most other things would probably just like spill or something, but water is a different breed. All right. So because of the hydrogen bonds, right, the positive versus negative bonds, this is the strongest type of uh, intermolecular bond. All right, but it has a high melting point and a high boiling point, which are respectively 0 degrees Celsius and 100 degrees Celsius. This is what the Celsius scale was based on when water turns into a gas and water turns into a solid. And ice is less dense than water, right? Remember what density is? Density is mass over volume. So that's why it floats on. That's why ice floats on water, and this is the only substance that does this. And it's very important that it does do this, or else, the life on Earth could most likely not be sustainable. Because if the water were to just freeze and sink, we'll just get a lot of ice instead of water. Okay. So let's go over this. And also, in the chemical structure of ice is that there is 4 waters bonded together. So I believe this is ice. One, two, three, four. Yeah, 4 waters bonded together. But in liquid water, there's 6 waters bonded to one another. So because 4 is more spaced out than 6, it's less dense, so it can float in water. All right, so calculating heat transfers. So this is an equation that represents the amount of heat something gets or loses. Okay, so it's a pretty simple formula. Delta Q equals delta mct. So Q is the energy that you gain in joules. M is your mass. C is your specific heat capacity. So these are all calculated values, like observed. So they're usually given on a test. And change of temperature in degrees Celsius. So change of temperature is the final temperature that you get minus the initial temperature. And your value of Q can be positive or negative. So if it was positive, that means it absorbed heat in from the surroundings, and if it was negative, it lost heat to the surroundings. So from the surroundings to the surroundings. And usually, what was I going to say? I forgot. And I always remember this as Q equals MCAT. But yeah, I believe in science 10, it is positive or negative, but in chemistry, usually worked in positives, although the concept is different. Okay, so let's move on to the next slide. So let me clear all of this around. Okay, so let's do a practice question. How much energy is released when 55 grams of water cools from 35 degrees to 12 degrees Celsius? So, this is our equation, Q equals mc delta T. So we know the specific heat capacity of water, 4.19 joules per gram Celsius. We want the change of temperature. So TF minus TI. We have final temperature. We have initial temperature. So 12 degrees minus 35 degrees. 23 degrees Celsius, negative 23 degrees Celsius. And then we have the mass, 55 grams. So we just simply plug it in. Q equals mc delta T. Q equals 4.1. Oh, sorry, I put it in around 5 grams here. I did 23 degrees Celsius here. So based on this, you can already tell that you'll get a negative value for Q. So that makes sense, right? Because if you're releasing energy, you're losing energy. If you're losing it, your net gain should be negative. So we will just plug these numbers in our calculator. So I have it beside me. Let me put it in. All right. And then we get, okay, well, very interesting. Why did I just do that? But the calculator, our raw value is -5300.35. And indeed, we have to round to three significant digits. So that will be, two significant digits. So that's 5.3 times 10 to the power of 3 joules. But you should usually state these questions in a sentence. So you would state the energy released is, to pretend that wasn't there, not negative times 10 to the power of 3 joules. You would just put a positive, you would just say positive. And the reason is because you don't want to, because that is just a that is just not how you say it, because you're still releasing a magnitude of energy. But by saying it's releasing, we know that the net gain or the net whatever is negative. Okay, so let's move on to the next slide. Okay, so um, these type of questions are the same. So we'll just go over this. So I'll just quickly say how to do it. So 120 kilojoules is your Q value. Uh, and it's the temperature is getting smaller, so this should be negative. Um, Seawater, we're gonna assume that it's regular. Well, we need the specific heat capacity of salt water, but I don't have that on me, so we're gonna say that's water. So you'll know what C is. You'll know what the change of temperature is. You don't know what the mass is. You need to find the mass. Your C value is in joules per gram Celsius, but you want it in kilojoules per gram Celsius. So I would convert this into joules. So to convert from kilojoules to joules, you multiply by 1,000 in joules, and then now you can use Q equals MC delta T. Isolate for M. M equals Q C over delta T. We have a negative Q value, a positive C value, and a negative T change of T value. That cancels out. So your answer, your mass will be positive. And that made sense because mass is a scalar value, but it also makes sense because we cross it out and we induce all of these properties of the change of temperature and stuff. Okay, let's move on. All right, so this is a challenge question, but we're not doing it. All right, so energy transfer in the hydraulic cycle. So I believe this is just like the rain cycle, the water cycle, right? So in the water cycle, things absorb energy or release energy, right? And things change. So it goes from ice to water to vapor, which is gas, right? And then there are some certain values of it. So these are the terms essentially. So the terms from ice, so something going from solid to water can be called fusion. Something going from water. I mean, no, I'm sorry, not for something. Only for water, these words apply. So vaporization is from liquid to gas, from gas to water, to condensation, and then um from water to solid, it is once again. I mean, water to ice, it is also called fusion. So to when okay, so if you think about it, so why is one of them positive and why is one of them negative? Well, think about it this way. When you heat up water, it starts to boil and turns into gas. So the more temperature you need, the more energy, the more heat you need. So the more energy you need, will make it more of a gas. Okay, so gas, solid, liquid, and the energy increases. The energy applied must be increased as you want to make it into the state. So what these values mean, 6.01 and 40.65, it means that per every mole of water you have, right, you need to apply 6.01 kilojoules to it so that it heats up. Okay, yes, that's it. Okay, let's move on to this one. Okay, so you see all this. This is just something interesting. Well, this is like, I don't think you memorize it, but it should be pretty easy. Uh, gas, solid, liquid, freezing, melting, common terms, condensation, evaporation, common terms, and sublimation is the one from gas to solid. This one is the only interesting one. Sorry. This one is the only interesting one. So, but it is literally called both the same. So this is actually pretty easy to memorize. These are all common. These are all common. It's just this, but this only has one name. So from gas to solid, both ways, it's called sublimation. Okay. Okay. So the formula for your heat of vaporization and your heat of fusion is you take is so is that you take the amount is that you take the amount of heat absorbed or lost, and you divide it by the amount of moles you have to find the heat of fusion and heat of evaporation. So the amount of heat it takes to make 1 mole of water or ice, of ice turned to water or water turned to ice. Okay, that is what it basically is saying. So a key note is that when the state of your water is changing, so your temperature does not change, and vice versa. When your temperature is changing, your state does not change, right? So when water is turning into ice, um, it changes at a certain temperature, which is 0 degrees, right? But the the temperature remains constant. But when you are changing the temperature of something, the state of it does not actually change. Okay. Okay. Term heat of fusion, substance of energy required to release or melt, freeze 1 mole of a substance. Vaporization is just vaporize a substance. So yeah. So Q over N. We went over how to do this. Okay. So let's see these questions. So we know the formula is H equals Q over N. How much energy is released when 2.05 moles of water vapor condenses at 100 degrees Celsius with no change in room temperature? Okay. Um, you isolate for Q, N times H, and you know your H value. Your heat of vaporization is 40.65, maybe. So I will just multiply 2.05 moles times 40.65 kilojoules per mole, and I should get the answer. All right. So I got 83.3. So three significant digits is 83.3. So let's go see this. Oh, okay. And it's negative because I should have added the sign, sorry. And it's negative because water vapor condenses. So it goes from gas to liquid, and we just demonstrated that from solid to gas, you need to add energy. So that means from gas to liquid, you do the opposite. So that means you release energy. So it should be negative. And this negative would come from the H value, negative. Okay. All right. And we know all this. Okay. So let's just quickly go over the water cycle. Uh, Evaporation. Water is from drawn up into the clouds from the heat of the sun. Inside the clouds, it condenses into water. The water falls down, and it's called condensation. And then the third step is precipitation. So 1, 2, 3. Yep, that's it. And all these things, it's basically saying, um, well, water in plants and from the earth is goes up by transpiration, and the runoff just means that when it hits the earth, it may flow and collect into like something else. Okay. Um. Yes, this is the water cycle again. Okay, let me erase my drawings. So I was going over that. Okay, easy. So human impact on global climate. So greenhouse effect. We emit greenhouse gases into the atmosphere, and some of the major ones are CO2. You probably heard that CO2 is really bad because it traps in the heat molecules, and we do that. A lot of our tasks, like driving and using electricity, does does promote more CO2 in factories. So basically, human impact is that because of our desire to have things that we don't necessarily need, like factory items and cars and luxuries, we are actually damaging ourselves and future generations. Because is there something in chat? Hold on, I cannot see the chat. Let me just iMessage you this. But yes, that is what human impact is. Yeah, so CO2, CH4, N2O, H2O, water vapor. All right. So, yeah, industry and electricity, automobiles, that's my CO2 example. Decay with the oxygen%. Livestock, yes, cows, they poop a lot. So that's why they produce CH4. N2O, I believe, is from like cars. Yeah, cars and fertilizer. Okay. All right. Which of the GHGs are not produced by automobiles? CO2, N2O, or CH4? It is CH4 because they are only made by cows and other things like that and gas pipes. All right, so how do we track CO2? Well, I'm pretty sure you measure like ice. Yes, you do. So you look at ice and things that have CO2 trapped in them from years ago, and you can see it compared to the average CO2 concentrations in other things, like the ice today compared to the ice sheets found millions of years ago. And we do see an increase of CO2, which can kind of support, which does support that the Earth climate change is real, unlike these fake people saying that it's not happening. So just some quick terms: anecdotal evidence. These are stories. These are things that you come up with yourself. It's not really evidence because you have no recorded proof of it. You're just saying it based off of memory. Scientific evidence. It's evidence. There's like um it's like hard evidence. It's like I forgot what the word is, but it's there's evidence there's proof, right? And you go through multiple scientific processes to verify that your data is accurate. All right, so the temperature is changing. All right, so all these things are just saying that scientists can track our future by looking at various data, such as carbon dating, and they can predict how bad the weather is going to be. And it is pretty bad because they predicted that at the end of 20 to 100. So 20. Okay, so 2000 and 2100, we cannot reverse climate change anymore, and it will increase by 1 degree. I think from now to 2100, it increases by 1 degree, which may not seem like a lot, but after that, it will skyrocket and it'll be uncontrollable.
Actually, that presentation, like that graph, is pretty old. The new prediction is the world's gonna essentially end at like 2050. So have fun, guys.
Actually,
Yeah,
oh,
I
oh
know.
yeah, it is pretty old. Oh, it is really old, isn't it? Wow. So we might end, but that's not my issue. That's their issue. So what are the effects? Well, obviously, climate change will make things hotter, and the sea level will rise. I forgot why the sea level rises. But anyways, the sea level will rise, right? And the sea level rises, homes get destroyed, crops get ran out, lives cannot, animal lives cannot be sustained, and all these things. Okay. So international efforts, you don't even know these at all, but we're just gonna put them here. Montreal, UN, Kyoto Protocol. I think you learn about Kyoto Protocol in social, but it's not important as well. Social is just not important in general, to be honest. But UN, I don't know. That is, I would say the main thing takeaway is that we are trying to make efforts to stop climate change, but obviously the national interests of nations today is other things, like they like their economy, they like government, they like political affairs, foreign policy, they like all these things over the environment. So don't expect much, please. All right, and this is just personal choices. You can reduce your impact on climate change by, well, planting trees, not really, but like, sure. Every little step counts if we all work together. So you see all these people wearing bikes, they are not emitting CH4 and CO2. I mean, not CO2. They are not emitting, no, not CO2, CH4. They are not emitting CO2 and N2O. So this will help reduce greenhouse gases. They are not using that much electricity. They're not using water and resources. So they are also helping global warming. And these folks are planting trees to reduce carbon dioxide levels because photosynthesis plants need carbon dioxide, so this is also helping. So you can make, so the main moral is be environmentally conscious. Use a hydro flask. Okay. Okay. And I believe that is the end of global systems. Yes, slide 58. So with that in mind, that is it. That is Science 10 in a nutshell, in a very large nutshell. But it was a fun experience to teach, and and I feel like it was a learning experience, highs and lows, but overall, it was not bad. But if we
Not
did
bad.
make, if we did make your learning experience harder than easier, we apologize. But it is. I feel like we did a simplification of everything, so don't stress, guys. Okay. Do you have any closing remarks to make?
No. So yeah, it was fun teaching you guys to the one person who showed up occasionally.
Yes.
Yes.
Um, yeah, that's it.
So yeah.
Okay.
Goodbye. Enjoy your online school, not really. Enjoy your winter break. Enjoy the rest of your 2020,
Yes.
2021. Until the end of your life at like 2050.
Yes.
See you all in heaven.
Yes.
Maybe hell. Tony's gonna be in hell, by the way, so you might see him there.
Bruh. Okay.
Okay.
Goodbye, boys.
Goodbye.